In theory, a turbo is simply a hot air pump that forces more air into the engine. With more air, the engine can generate power more efficiently, improving performance, reducing fuel consumption, and cutting emissions. The turbo is mounted in the exhaust system between the exhaust manifold and the exhaust pipe. As exhaust gas exits the engine, it drives the turbine, which turns the compressor, pulling in air and compressing it. Oil passes through the turbo, providing vital lubrication. In practice, the turbo is a highly efficient, complex piece of engineering, built to tolerances of thousandths of a millimeter. It comprises a turbine and compressor connected by a shaft supported on a bearing system. The turbo is driven by the waste energy from the exhaust gas. The exhaust gas enters via the turbine housing, turns the turbine, and leaves through the exhaust outlet. Exhaust gas temperatures can reach 950 degrees C, which means that special high-temperature materials are needed for the turbine wheel and housing. The speed and load of the engine determines how fast the turbine wheel spins. With the engine at idle, the turbine spins at minimal speed. As more gas passes through the turbine housing, the turbine rotates faster. At full speed, the turbine wheel can rotate at up to 240,000 RPM. The compressor wheel is connected to the turbine by a forged steel shaft and is powered by the spinning turbine. Air is drawn into the compressor housing by the compressor wheel and is compressed as the blades spin at high velocity. The shape of the housing converts the high-velocity, low-pressure airstream into a low-velocity, high-pressure airstream at the outlet. Air enters the compressor at ambient temperature, but leaves it at up to 200 degrees C. As air temperature increases, its density decreases, which reduces power. So it's usually passed through a charge air cooler or intercooler, which uses air or water to cool the hot, high-pressure air. The forged shaft linking the turbine and compressor runs in a bearing housing, lubricated by oil from the engine. The oil is fed under pressure into the bearing housing to the journal bearings and thrust system. The oil also acts as a coolant, taking away heat generated by the turbine. The journal bearings float on a film of oil between bearing and shaft and bearing and housing. The clearances for these oil films are critical. At both ends of the bearing housing are unique oil seals. Totally unlike normal engine oil seals, they're specially designed to cope with the turbo's extreme temperatures and pressures and help ensure that oil does not leak into either compressor or turbine housings. A small turbine will give a good response at low engine speeds. However, at higher engine speeds, it can overspeed and overboost the engine. To prevent this happening, some turbos are also fitted with a wastegate to control boost pressure. As soon as the pressure reaches a preset maximum level, a valve opens, allowing the excess exhaust gas to bypass the turbine wheel and go straight out through the exhaust. In a wastegated turbo, the turbine wheel can safely be smaller, giving better engine response and yet still maintaining maximum power output. Turbos with or without a wastegate can be successfully stripped and remanufactured, as long as the manufacturer's exacting specifications are followed and genuine new replacement parts are used. All remanufactured turbos supplied by us use genuine new replacement parts and are to OE standards. In conventional turbos, the amount of airflow into the engine is determined by the design of the turbine and compressor wheels and their housings. This design is inevitably a compromise between its performance at low and high engine speeds. An even more effective method of adapting turbo characteristics to improve engine performance at all engine speeds is the variable turbine turbo. Depending on the manufacturer, variable turbine turbos use moving vanes or a moving nozzle to alter the turbine stage while the engine is running. This allows more efficient use of exhaust gas energy and airflow to provide the desired boost level across the widest range of engine speeds. This improves response across a wider engine operating range, improves fuel economy, enhances engine braking, and allows vehicle manufacturers to use smaller engine packages to achieve a given power output. Early variable turbine turbos used pressure or vacuum actuators to regulate the position of the vanes or nozzle. Most modern units use electronic control, governed by the engine management system, with the turbo having its own ECU. The complexity of variable turbine turbos means they cannot be successfully remanufactured with an absolute guarantee of accuracy or reliability. Consequently, we only supply brand new variable turbine turbos.